Next, let's talk about how to learn the parameters and hidden variables in a collaborative deep learning model or the CDL model. Remember that in the previous latent vector models, in the previous lectures, we basically have this objective function where we have the first term as the prediction error and the last two terms as the regularization term, basically to regularize these P and Q so that the model will not overfit. And similarly, to learn the CDL model, we basically formulated as trying to maximize the posterior probability of all these parameters like U, W, B, and V. And this is actually equivalent to maximizing the joint log likelihood as laid out in here. And specifically, this first several terms actually corresponds to the prior term or the regularization terms for the user vectors, the weights, and the biases. And this is actually very similar to the last two terms in the previous latent vector model. And this term corresponds to generating the item latent vectors from the content representation with a Gaussian offset. Remember that in the previous model, we assume that this item latent vector is actually generated from a Gaussian distribution center at the middle layer representation of the autoencoder, right? So this link corresponds to this term. And this term basically, it's a L2 loss to encourage this latent item vector to be close enough to the middle layer representation of the SDAE. And this term corresponds to generating the clean input from the output of the probabilistic stack denosing autoencoder with the Gaussian offsets. So this is actually corresponds to the last link here. And this is the key part that enables us to learn this stack denosing autoencoder. So without this, we cannot learn the deep learning part of the model. And this term is the probabilistic part of the deep learning model. Basically, it corresponds to generating the input of layer I or layer L from the output of the layer L minus 1 with the Gaussian offset. So basically, this is just L2 loss to encourage that the input of the next layer, which is here, is close to the output of the previous layer. Without this, we actually will have a deterministic autoencoder where the output of the previous layer is equal to the input of the next layer. And the last term is the prediction error term. So as we mentioned before, this is the error between our predicted rating and the ground truth rating. And the C here is actually very similar to the sum over the training set here. If we have a existing rating or an observed rating, the C here will be relatively large. And if it's just a missing rating, and we will pretend that the R is 0, and we set the C to be very small. So again, this term corresponds to the first term of the previous latent vector models that we talked about. And we can actually have a simplified version of this model by simply setting this lambda s to positive infinity. And if we do this, the likelihood was simplified to something like this. And this is just basically saying that the encoder part will be generating the encoding that's close enough to the latent item vector B here. And this F here is a function that denotes the encoder, basically the first half of this autoencoder here. And this FR denotes the whole network. So basically it's an encoder plus the decoder. It's the reconstruction of the content from the corrupted content. So this is the simplified objective function if we want to learn this model. So basically with this objective function, we can try to basically minimize this objective function such that we can find the correct u, v, and w here. And in order to do this, we need to resort to a hybrid optimization scheme of block coordinate descent, a backpropagation. So basically, we will alternate between updating U and V, which is the latent vector model part, and updating the weights and biases, basically the W and V. To update this U and V, basically we will just take the derivative of this objective function with regard to U and V, and we'll set the derivative to 0, and then we can solve for the corresponding U and V. And this is the updating rule here. And this specific term here actually corresponds to our deep learning part. Without the deep learning part, this term would just be 0. And to update W and V, basically the deep learning parameters, we will use a modified version of the backpropagation. And this is the equation.